Welcome to the On-Premise IT Roundtable podcast, the only show that dares to be both on topic or on premise, and sometimes on location or on premises. Each time we meet, we bring together a group of IT luminaries to discuss a single concept. In this episode, we're talking about the future of storage, and maybe there isn't a future of storage. But before we begin, let's quickly meet who's on the panel today.
My name is Jawad Khan. I'm a principal engineer with Intel with about 16 years of experience in storage and memory. And today we are going to talk about a competition that we won with persistent memory and Intel. You can find more information at the end of this at intel.com/Optane.
I'm Frederic Van Haren, and I'm the founder of Highfence, a company that provides consulting and services in the HPC and AI markets. And you can find me on Twitter and LinkedIn as Frederic V. Haren.
And I'm Justin Warren. I'm founder and chief analyst at Pivot9 Consultants and Advisors.
So as somebody who's done a lot of work on storage, in fact, that's been my the foundation of my career, it sort of pains me to say this, but truly the only reason we even have storage is because we didn't have enough memory. If we needed there to be persistence, well, we could have achieved that with some sort of persistent memory capability years and years ago, if only we had enough of it. Well, that's sort of the pitch in my mind for a lot of what Intel has been doing with this Optane technology. And that's why when I saw Jawad present this finding, I was really, keyed in on it, because frankly, the idea that a system with sufficient memory doesn't really need storage is pretty radical and revolutionary. So I'm going to hand it over to you. Tell us a little bit more about the setup, the competition, and the results of using Optane like this.
Yeah, so this competition was around big scale similarity search. Similarity search is basically a class of problems which are prevalent in AI, where you have to find things which are similar to each other. It's also found in recommendation system or ranking systems. And these are like large scale problems, like billions and trillions of items that you have to go in and search for something with the customer or the query wants you to find, which is similar to the thing that they're asking you to find. And in order to showcase the Optane and Intel technology around this domain, we entered a competition organized by NeurIP's 2021 conference. In that, we participated in a track, which is basically the custom hardware track. And with around a $15,000 server with Intel Optane technology, we were able to come in first in the cost or the CapEx plus OpEx metric, which is mostly the best metric that I feel that showcases the balance of system that you can put together. Besting an NVIDIA system, DGX A100 based system, which costs anywhere from $150K and above. So if you are able to customize your software and hardware, you can get some very interesting solutions put together for problems where people don't look at these type of solutions, where you can put your entire data set in the memory.
It seems like the combination of Intel Xeon and persistent memory makes you really competitive, and certainly from a price perspective. I mean, the price comparison with the DGX is enormous. So what do you feel is the most important factor? Is it the Xeon? Is it persistent memory? Is it a combination of both?
I would say it's a combination of both, but in particular, I would put the emphasis on two things. One is persistent memory, which gives you a large memory space, in this case, 2 terabytes or more per core. And then if you can tailor your software to utilize that large capacity that is now available to you, and which could be made persistent, so you don't have to page in and out anything from storage. You just keep your entire data set and the graph. In this case, it was a graph-based algorithm that we chose to compete with for similarity search. Your entire graph just stays in the persistent memory. You don't have to bring in pages from the storage. And if you do that, you come out ahead.
How useful is that really though? Because there's a lot of software out there that has been written over the last couple of decades that assumes that there will be some kind of file system or storage that I need to address. How much of that software has to get changed before it's usable with something like persistent memory?
So in this case, it's the algorithm itself was based on a Vamana algorithm from Microsoft, which has been open sourced. So we tweaked it. We make modifications to it so that we can take full advantage of the persistent memory. If you want to, and you can always certainly keep storage in play if you want to. And there is a specific algorithm called diskANN also from Microsoft, which has been open source, which is almost entirely disk based. But then the performance suffers. You're kind of limited in the number of queries that you can service. But if you are open to making some modifications, and in the minimal case, and we made two different solutions. One was just a minimal software change, which basically was about 50 lines of code to their Vamana algorithm. And we were able to get significantly higher, like 2x better performance just by that simple change. But in order to win the competition, of course, you have to go and overhaul that algorithm to truly take advantage of the persistent memory that is there. So it's up to the organization how much they want to delve into it.
So you're talking a little bit about the software like Graphan. Is that available to the public? Is that internal to Intel? Can people use it?
Yeah, GraphANN is our solution or our modifications or updates, which basically allow you to use this large scale similarity search solution with persistent memory. We are in the process of open sourcing it. It has not yet been open source, but we are going through the process, internal process to get it out there. So anybody who has persistent memory and Xeon can use that algorithm.
Yeah, so I guess that's what I'm sort of getting at is that on the one hand, we need this stuff to be open sourced because some of this will require modifications, but that also implies that people are able to make that. Most people and most organizations just buy stuff. We don't actually want to write a lot of code. I mean, I write code, but I haven't written anywhere near most of the code that I use every day. And quite frankly, no one really wants to use the code that I write these days. So it feels like, okay, great. We've got some hardware that we could buy that we could use if only the software worked, but it doesn't yet. So how do I unless I'm a niche organization who wants to use some sort of similarity search and I'm in this particular field, is this something which is actually practical outside of that? Because I would love all my stuff to not have slow storage. Storage is just slow memory.
Yes, storage is slow memory, and in the limit, the best storage is no storage. That's what I believe in, and that's what I've been working in all through my career to make happen. Persistent memory or PMEM is closest we have come to that kind of a situation. So the software, to answer your question, the software piece is really based on what the organization or the company that is involved in this large scale similarity search wants to do. And these are big companies like Microsoft, Facebook, Google, eBay, Pinterest, Twitter, because all of these guys, they at some stage in their pipeline, they do similarity search one way or the other. And if I look at that, then it's really dependent on what the kernel that does the similarity search is that optimized or not, given whatever hardware you're throwing at it. So based on that, for somebody who's an enthusiast and doesn't have like trillions and trillions of these data vectors that they want to search through, maybe a diskANN based solution is good enough, but it will not scale to the performance levels that we were able to demonstrate with this solution. The use case is pretty broad. It has many different companies that use this. Anywhere where you are recommending a product, you're recommending a person, you're comparing pictures, audio, text to something that the user generates, that's where similarity search comes in. And the way internet and the data on the internet is growing, it's growing anywhere from 3 to 4x every year that these large search engines need to search through these items that are being generated every day or every second.
So to a certain degree, you could say that software enables innovation, right? The hardware innovation. Can you talk a little bit about the effort that Intel is putting in building software, as in containers and so on, for the customers that buying PMEM? I mean, buying PMEM by itself is not the end goal, right? It's the combination of the software and the hardware. So you talked a little bit about Microsoft and I assume, you know, Red Hat and others from a Linux perspective. Does Intel also have a software initiative?
Yeah, Intel has software initiatives, and we deliver all these different types of benchmark solutions or other solutions that you can look at and see how we have used a persistent memory. There's a software tool called Persistent Memory Development Kit that you can use, PMDK. That basically abstracts some of these nitty-gritty low-level details that you don't need to worry about if you use the appropriate functions there. And as this effort shows, my team was able to put together the solution and eventually win that competition with relatively modest software resources. We were like 3 people or 4 people who were working on it actively. So from that perspective, we put together these solutions and showcase that, look, these things are possible if you have the right hardware and the right algorithm to meet that hardware.
I think you said something earlier is very interesting. So first of all, I believe that the competition was with a single server, right?
Yes. So all of these competitions, by the structure of this competition, the way it was put together, was basically on a particular metric, which was basically CapEx, 5-year OpEx. And then for 100K queries per second, that's the kind of the performance level that they wanted us to meet. You can throw however many servers at it, as long as you can deliver 100K queries per second. And then the final piece was 90% 10 recall at 10. That is like a metric of accuracy of how accurate your results are in this billion scale data sets. And there were 5 of those that were donated by different companies, including Microsoft, Facebook, and Google. So you had to go through all of these. These had different characteristics, different distributions, different distance metrics, and basically win across these different metrics that were put on the competition.
So I assume there's a fine balance between cores and persistent memory. This was a single server. If we think about clustering those servers, what do you feel is the limiting factor? Is that the amount of cores, or is it the amount of persistent memory?
I would say it's the amount of persistent memory, because the main aha moment for us when we started working on this was there are 2 parts to this solution. One is called the graph, which is basically all of these billion points. We do something which is called an indexing step at the beginning. Once these vectors, which usually come out of a deep learning pipeline, these are high dimensional vectors, you put them in a graph so that similar vectors occupy closer locations within a graph. And once you have this index built, then when the query comes in at runtime, you go and try to search through this graph and try to find what are the 10 nearest neighbors or n nearest neighbor or k nearest neighbors to the particular query. So what we found was, if you are able to put your entire graph in persistent memory, you don't have to page in and out anything. And you can keep your vectors, which are usually much smaller than the graph, in DRAM. So then you utilize the best of both worlds. The DRAM gives you fast access to these vectors, and then the graph in its entirety is sitting in the PMEM, and therefore you don't have to touch the storage. And if you take one step forward, which means that you make this graph persistent, then you just come up and you are up and running. You don't have to page in anything from storage. Obviously, in this case, we did not do that because we had to showcase what is available what you can do today. But obviously, if you have a persistent memory, one of the premises is that you can definitely use it for persistent storage without actually touching real storage. So that was how we did it. So I would say, if you keep on increasing persistent memory, the vectors per node density goes up. So you can basically have more vectors. In this case, there were like about 1 billion vectors that were sitting on this one node. You can go up to 3-4 billion vectors on per node. And then if you have, let's say, 1 to 2 trillion vectors that you're searching through, then you shard them across all these different systems that people usually do for these type of scales.
Where's the persistence part coming in? So what, like at the moment, it feels like you've got persistent memory, but it's really being a memory layer between DRAM and other storage, because it's faster than storage, but not quite as fast as DRAM.
Yes.
But it's also cheaper than having the same amount of DRAM.
Exactly. So so it's in the sweet spot between DRAM and storage. So performance-wise better, as you said, compared to storage, but cost-wise is also better compared to DRAM. So
it's cheap, slow memory.
Cheap, slow memory, yes. And that is important to keep in mind, to utilize that particular aspect, that it is cheap, but also at the same time, it is slower than DRAM. So you can't just throw in a persistent memory and say, now I have 2 terabytes of fast memory. That's not the case. In reality, you have two different types of memory. One, DRAM is faster, but smaller in capacity, and you have persistent memory, which is slower but extremely large in capacity, and cost is cheaper in cost. So that's where the solution comes in, that you have to put right stuff where it belongs, so that you get the overall solution can be optimized.
So it sort of goes back to that software part, but the software becomes really important, because this is sort of worse now. Yes, it's faster storage, which is nice, but now I've got another layer, and it's like, so many layers here, and I've got to worry about where my stuff goes. And because I don't have 2 choices, I've got memory. It's either stuff I'm operating with, or it's over there somewhere, I'll use it later. Now I've got this halfway point, which is not quite either of those things. So I've got to radically rethink how I do software design. And this is something like you mentioned a few companies that would use this. It's like, they're all massive global, billion-dollar companies. I'm sort of looking at the enterprise market, where you're going, okay, most of the stuff there is just, we buy what comes off the shelf. And we are not in any way ready to do that kind of software engineering. These are companies that struggle with SQL queries. How are they going to get, is this something we have to wait a while till people figure out how to create the software in a nice productized, packagey way? Or is this something that you would use if you're an enterprise, like you need your team on this, but they're going to have to spend some time working on the problem? This is not something you can just pick up, buy from Intel, put it into a $15,000 server, and away we go.
Yeah, so we are not selling this software. So what you said is true. If you are a small shop, then you have to make a decision whether this kind of solution or performance is actually what you need, right? Most smaller shops probably don't need to search through 1 trillion items. It's a pretty big space. But if you have like a billion scale data set or billion items that you want to go through quickly, then 1 server should be enough, just as we showed in this competition, right? But if you as you go above, then obviously now you have to pay the price and do your software. To your other comment earlier, I would say that when you write software, it doesn't become more difficult. It's actually simpler than going through a storage stack, because persistent memory is exposed exactly like a memory. It sits on the DRAM bus, and you access it exactly like a memory. The only thing you have to worry about in this case is a particular range of that memory might be slower than this other range, which is smaller, which is sitting in DRAM. So I would say that actually your software would become simpler if you cut out the storage from it, right? which is exactly what we experienced as well. Making all these changes, we didn't have to touch the storage stack at all, because the whole thing, once loaded into persistent memory, was there, and it was there for the duration of this test.
Oh, okay. Yeah, because I mean, getting rid of the storage part, like, yes, it's horrendous. It's layer upon layer of old primitives that, like, LUNs need to die.
Yep. Block based, and so
so being able to just say, look, like mem copy or something, and
exactly
access a particular range, that is probably, like, you could, I can, even I, a terrible programmer, can imagine how I would say, okay, these arrays or whatever live over in that bit, and then these other arrays, they're my persistent part. They're a bit slower, so active set, not quite so active set. But now I don't have to deal with any kind of IO stuff. File control, and the permissions are wrong. Now everything's broken.
So
So we have to talk about storage, right? So in your opinion, how much PMEM do we need to have in a server before we can stop talking about storage?
Storage. That's
Intel. They want us to sell all of it. Just buy all the PMEM.
Yeah, we sell both of them based on the Optane technology. We have a storage solution, SSD, which is based on the same memory technology, which goes into persistent memory. For those cases where you can't get rid of storage just yet, I would say it's really up to the use case, right? For example, is 2 terabytes enough per core, or 4 terabytes enough per core, or 10 terabytes enough per core?
40K should be enough for anyone.
Well, that's a few decades ago, right? So when I was in undergrad or something.
Yeah, we'll always want more. Like as you mentioned, the data growth. People have been saying, oh, data is growing. It's on an exponential rate. We've been saying that for decades. People are not going to create less information. I wish they would, but people just keep wanting to talk to each other and take photos of things and put sensors into everything for some reason. So yeah, the amount of data ain't going to go down. So I'd say anything that you say now of like, okay, 2 terabytes per core, like that's going to change. Like we're going to want 10 terabytes per core before you can blink.
Yeah.
So can you work faster on this, please?
We are trying our best. Yes.
Yeah, I think that the traditional and historically, the challenge with storage, or the problem with storage, is that no matter the size, being it kilobytes, megabytes, gigabytes, terabytes, petabytes, people will find a way to fill it, right? That's the challenge with storage. So we're at the point now where keeping storage, it's not a cost problem anymore. It is more a data management problem, which is a whole completely different problem. But I do believe that persistent memory, certainly for AI, is a big deal. If you talk a little bit about the competitors you saw in the competition, is they have similar problems, right? They have compute on a card, and their challenge is also to have as much memory as close as possible to the compute. So that problem doesn't go away. And that's, coming back to one of my earlier questions, is it's a fine line between the amount of cores and memory, right? And the more memory, the better, because anything you can do in memory, even if it's a little bit slower, but you have the capacity, gives you tremendous advantages. Because still going to storage is there's also a cost, an access cost to storage, right? There's multiple layers there too.
Yep.
We talk about the software, but there are drivers and layers on top of it, and RAID and erasure coding. All of that is not just a storage problem, it's also a compute problem. Erasure code and RAID is all calculated. So I do think that persistent memory has a great advantage in AI. The question is, how much can you squeeze into a box such that its advantage is really superior to any other solution?
Because that's a good point there around the capacity that's close enough, because not just the storage, but also anything further away is over a network.
Yeah.
And as you mentioned, storage has grown really, really quickly. But one of the issues is the access speed. And if it's not local to the CPU, like if it's not on the local bus, it's light years away. In terms, relatively speaking, it's just so far away. So having it close, like I know that Intel has recently been talking about longer roadmap stuff around things like CXL. Are we going to be limited to stuff that is only in the chassis, or are we going to start going beyond, like putting memory close to the CPU won't actually have to be in the one single server?
Well, there are things that are in the works that I'm not at the liberty to talk about right now, but you can see the progression, the way it's going, and the way the memory capacities are growing. I would add to your comments one more thing. Performance and speed and cost is just one aspect. The other bigger deal is power. So as you keep on putting your stuff out at a further distance away in your data center, your power to bring that data closer where the actual compute is happening goes up. So for example, in this case, in the competition case, we were able to reduce the power consumption by 5x by keeping everything in the persistent memory closer to where it was needed, instead of just bringing in everything from the disk.
Yeah, but I think from a power perspective, I think what you're doing is you're trading raw compute power, and when I talk about power is the wattage versus memory, which is much lower power consumption. So it's a negative trade-off from a power perspective. Negative in the sense that you consume or you need less wattage to obtain the same result.
Exactly. That's exactly what happened.
Forgive me if I'm wrong, but it's the old thing of trading space for time. So you pre-calculate a whole bunch of stuff and then just store it, which if you didn't have persistent memory, you wouldn't be able to do.
You wouldn't be able to.
Yeah,
exactly.
So I don't have to run calculations anymore, because I do them once and then I just keep the results.
And keep the results close by, not over some network or somewhere else where you have to bring it in piecemeal and look at it, right?
So in some ways, nothing's really changed except for the hardware. So we have hardware that we didn't have. So we're kind of circling back around and going, oh, the software is really important. It's like, no, it's the same software, same primitive, same ideas.
Yes.
But the hardware is different. So the hardware is actually really important.
Hardware is important. I'm a hardware guy by heart. that's what my PhD was in. So that's the piece that I always focus on first before I start jumping into the software domain. But at this stage, it's a combination of both. But if you would have asked me, without this hardware, can you build this? Probably the answer would have been no.
So I'd like to basically get us back to the premise here. And I'm going to ask you all, now that we've spent half an hour discussing this, think back to where we began. Sometimes the best storage is no storage. Are you on board with this idea? Justin, has he won you over? Is the best storage no storage?
Yes, I think we're just changing the name of what storage is. Originally, storage was core memory, which was persistent memory. We just didn't have enough of it. What we're getting now is we're getting more better memory. So yes, I think if we can finally go back to the future and have nothing but memory, and memory will be storage, that is all we will need. I don't think we're ever going to get there though, because people keep creating too much data. Stop creating data, then we won't need as much storage.
Frederic, what do you think?
Yeah, I'm a big fan of persistent memory. I mean, not just now, but also from the early days, right? I mean, it's memory makes all the difference. And the example I like to use is when people are saying that their laptop is slow, the tendency is to think that it's a CPU thing, right? One more cores, while in reality, the bottleneck in most cases is that applications are so memory hungry that the lack of memory is actually causing the performance issue and not the CPU. And so, but I agree with Justin, right? The amount of data being created is growing exponentially, and hopefully the technology will be able to grow as quickly. But I'm happy to see that persistent memory has made it through. And certainly for use cases like AI, I think persistent memory will make a big difference. And the good news is it doesn't cost you more.
And Jawad, I think I know where you stand on this question.
Yes, in the limit, I would say best storage is no storage. And we are furiously working towards making that a reality, starting with persistent memory today and many other things to come in the future. I would also like to say, if you want to learn more about this topic and particularly this competition win, you can go to intel.com/Optane, where we have a paper that you can look at, and that has all the details about the competition and the changes that we made to the code and results.
I'll also mention that you can learn more about this if you search for a YouTube video from our recent Storage Field Day event, where we have Dr. Khan joining us to present these same findings, and we go through it with the Storage Field Day delegates. So from my perspective, I would say I would remind you all of the Foskett's law that I invented and named after myself, which is that data tends to expand to take up all available storage. And I think that any attempt to constrain the growth of data is foolish. I think all we need to do is just try to use what we have as efficiently as possible, because we're never going to outrun data. So before we go, we just heard where we can find this white paper. Where can we continue this conversation with you?
So I'm on Twitter at KhanJB. And also on LinkedIn, you can find me there.
Great. And Frederic?
Yeah, I was a delegate at Field Day a few weeks ago. And so if you want to follow up, please have a look at the recorded sessions. I'm also a co-host on the podcast Utilizing AI, which has very interesting topics with Stephen. And you can find me, as I mentioned, on Twitter and LinkedIn at Frederic V. Haren.
And Justin?
And you can find me on Twitter at JP Warren, or you can visit our website at pivot9.com.
And as for me, you can find me at S. Foskett on most social media sites, or Stephen Foskett on LinkedIn. And as Frederic mentioned, at AI Field Day and Utilizing AI and the rest of the Tech Field Day and Gestalt IT properties. Thank you for joining us for the On-Premise IT Roundtable. If you enjoyed this discussion, please remember to subscribe, rate, and review the show in whatever podcast application you use, since that does help our visibility. And please share it with your friends. This podcast is brought to you by GestaltIT.com, your home for IT coverage across the enterprise. And this special episode was sponsored by Intel. For show notes and more episodes, go to GestaltIT.com/podcast. Thanks for listening, and we'll see you next time.